Hello, my name is Olivia. I'm going to be doing part 1 of exam 11 where I walk you through the DNA replication and all that jazz. I'm going to start off with just drawing a double stranded DNA molecule, just so you know what that is. Okay. The whole point of DNA replication is to separate these two DNA molecules by copying these two strands. So, I'm going to erase. The first thing I'm going to do is explain how these two strands get pulled apart. So, there's that. That side looks a lot awful, but you get the point. What you are looking at is two single-stranded DNA molecules that were pulled apart by the first enzyme called helicase. As it's getting pulled apart, both forks are getting uncomfortably tight and wound up on either ends, and that is because helicase grabs the middle and starts pulling. And the origins of replication, where it starts expanding, is going to be right here and right here. And actually showed us a really cool example with a rubber band, and she started twisting it, and it looked exactly like that, and I was like, whoa, that's pretty cool. Anyway, gonna erase this. Actually, no, I don't need to right now. So while helicase is pulling from the origin of replication, the second enzyme called, and I cannot pronounce it for the life of me, so I'm just going to spell it, because I don't want to butcher how it's actually supposed to be said. I think it's topomers, but I'm not entirely sure. Anyway, so here's that. So it's going to be right here and right here. So this topomer starts making little nicks on each side of DNA, right here and right here, that is overwound or super, super tight. And what it does is on either side of the DNA that's overwound, it lets it unwind and it attaches it again. So kind of from what I understand, it unravels itself. Well, it unravels the DNA so it doesn't become too tightly wound or damages it. Like Helios, this and this, they work so well together and they can't be without the other, which is really cool. So I like that part a lot. I'm going to erase now. Sorry. I'm out of breath and I don't know why. Okay. So now the first two unwinding enzymes are completing their roles. I am left with a replication bubble, which would look a little bit like this. You know what? I'm going to redo that because that's ugly. And I want it to be blue. So we're going to go I like that one a little bit better. I like to have a lot of room. Anyway, it actually kind of looks like a transcription bubble, but it isn't. Anyway, I'm now going to label the strands on either side to indicate there are two separate strands. So this is going to be 5, this is going to be 3, and then this is going to be 5, and then this is going to be 3. And I didn't like how that looked. I only have 15 minutes, so I don't know how much time I have left. Anyway, now we are going to dive into the next two enzymes that are responsible for actual replication itself. The third enzyme, called primase, which is personally my favorite enzyme, and I'll show you in a minute. We're actually going to make that pink. It comes into the big bubble in the middle, and right at the point of origin on both ends, it'll start placing like, a couple nucleotides and complementary to the top and bottom strands. So we'll just put 1, 2, 3, 4. 1, 2, 3, 4. Perfect. And then we'll label it 3, 5, 5, 3. Okay. So now, what these primers are made for, what these primers are made of is going to be RNA and or ribonucleotides. So now once these primers are inside the bubble here, it will allow the fourth enzyme, DNA, and we're going to make this guy green, just so it's just easier for me to categorize all of this. So the fourth enzyme, sorry, it's going to be DNA polymers. It's probably spelled that wrong. Number 3. So it'll go ahead and see that there are 3 prime ends, and they are anti-parallel and complementary to each other. So it can help by now adding to the 3 prime ends. So, and start building a complementary strand, which is nice. So it'll start from right here and go up here, and then it'll start from right here and go right here. And what these complementary strands are called, this is called a leading strand. And this is also called a leading strand. Boom. Okay. I think I'm not missing anything. These green arrows are also indicating that it's a leading strand. It's called a leading strand because it's starting at the prime end of the primase. Unfortunately, it doesn't just end there. We have to replicate the other side, and since you can only add to the 3' end hydroxyl group, you can't add to the 5' prime end. DNA polymerase 3 is unable to do that, unfortunately. So now we have to replicate the other side, and we have to find the 3' end. And since there are since the other ones are occupied, we have to make another primer. And the reason why primase is my favorite is because you can just go ahead and do this. You can put one right here. And you can put one right here. And what these do, since enzymes are reusable, this happens on both top and bottom, but the bottom strands go from 5 to 3, and these go from 3 to 5. And you know what? I think I'll just put one right here. And I'm pretty sure this is 3 to 5, and then this one's going to be 5 to 3. So what this does is just boom, 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 boom. Sweet! I love how beautiful this looks. Primase and DNA polymers are working together to replicate. All these on these 2 sides are called the lagging strands because DNA, or the leading strands, have to wait for DNA polymers number 3 has to wait for primase to start creating. So naturally, this would be called the lagging strand. Lagging is also here. Boom. Beautiful. The lagging is also built in an, what is this? Oh, there's something else. I just know it, but I'm spacing. Give me a minute. Okay, yes. This right here, all of this is going to be built in an Okazaki fragments. So, Okazaki fragments. Basically, they're just little pieces, but the person who discovered it decided to name it after themselves, which is totally fine. But they're both on both sides, so just remember that, I suppose. Okay, and that is DNA replication. Everything has to work together. But since the primates are made of RNA, we don't want RNA mixed in with DNA because that would be very, 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 very bad. How they come out is with our 5th enzyme, which is our DNA polymerase 1. So think about it like this. The DNA polymerase 1 comes in and sees the primase and takes it out of the RNA and replaces it with your good old-fashioned DNA. So it ends up looking like this. The arrows are still there, but just to give it, I just need to erase it all. You have a top OR, you have a top OR. And lastly, our sixth enzyme, ligase. I don't know how to draw this, so I'm just going to tell you that I know what it is. Ligase and DNA polymerase 1 are basically the cleanup crew, and their roles, ligase's roles consist of sealing the recombination fragments or the Okazaki fragments, and then DNA polymerase comes in and takes out that primase because we don't want RNA and DNA mixed in with each other. So those are our six enzymes. We have, oh, if I can remember all of them at once. Well, I can't. The first two are for replicating. No, the middle two are for replicating. The last two are for cleanup, and the first two are for making that bubble and starting to clean everything up and stuff. It's the beginning. So I hope this is good enough. I think I covered everything. Thank you very much.